welcome to my lecture series. In my last class, we have seen that if V be a finite dimensional vector space over a field capital F and if B equal to alpha 1, alpha 2, alpha n be an order basis for V, then there exists a dual basis F1, F2, Fn for V star such that any linear functional f on V star can be written as linear combination of Fi, where the coefficient of Fi is the function value at alpha I, and any vector alpha can be written as linear combinations of alpha 1 to alpha n, with the coefficient of alpha I is basically function value of Fi at alpha please. So, let us give an examples and see it please. So, let me consider one examples. Let V be the space of all polynomial function of degree less than equal to 2 and over the f please. When polynomial function are defined from f to f only and the degree of the polynomial function is less than equal to 2. Consider T1, T2, T3 be any 3 distinct constants from the field capital F that I consider. So, let me define linear functionals on V please. L is equal to linear functionals on V. So, Li of P equal to P of Ti, I equal to 1, 2 and 3. So, Li is basically map from your V to your field please F. So, for I equal to 1 to 3, I have 3 functions. In my last lecture, we have already seen each Li the way I have defined is basically linear functionals. So, I have 3 linear functionals. So, this means that L1 of P equal to P of T1 and L2 of P is equal to P of T2 and L3 of P equal to P of T3. This one claim L1, L2, L3 the set the basis is a basis of V star. To show L1, L2, L3 be a basis, I have to show the linear independent. So, basically it is a linearly independent set. Since dimension of V equal to dimension of V star equal to 3. So, if I have a 3 linear independent element of V star, certainly they will form a basis. Now, to prove this is a linear independent, let me consider linear combination of L1, L2, L3. So, for any linear combinations is given by C1 L1 plus C2 L2 plus C3 L3. Suppose this is equal to 0. I have to show that C1 equal to C2 equal to C3 equal to 0 is the only solutions. This implies that C1 L1 plus C2 L2 plus C3 L3 operating on P, any element of V will be equal to what? C1 L1P plus C2 L2P plus C3 L3P, which is equal to C1 P T1 plus C2 P T2 plus C3 P T3. So, if I say that this is equal to 0 functionals, then definitely for any element P belongs to capital B, it will map to 0. So, this is equal to 0 please for any P belongs to your B. So, in particular for the set 1 x square, we have sigma C I L I when this is operating on 1 has to be equal to 0, that is C1 plus C2 plus C3 equal to 0. Sigma C I L I operating on x has to be 0, that is I will have what? C1 T1 plus C2 T2 plus C3 T3, this has to be 0, and sigma C I L I x square, that is equal to 0, that is I will have C1 T1 square plus C2 T2 square plus C3 T3 square equal to 0. Suppose this is the system. So, this implies that I will have 1 1 1 T1 T2 T3 T1 square T2 square T3 square, this into C1 C2 C3 0 0 0. My claim is that the coefficient matrix is basically non-singular. Okay. So, for that I have to check 1 1 1 T1 T2 T3 T1 square and T2 square T3 square. If I consider this one, if I do the elementary row operations, I am getting what? I am getting 1 1 1 and this is 0 T2 minus T1 T3 minus T1 and this is 0. So, I will have T2 square minus T1 square and T3, this is square, T3 square minus T1 square. So, I will have this one. Then again one more step, if I go, then I will have this is equal to 1 1 1 0, this is T2 minus T1, I will keep it as it is because since T1 T2 T3 are distinct, so certainly T2 minus T1 is non-zero. So, I will have this and T3 minus T1 and this one I have to make it 0. So, if I multiply T2 plus T1 to the second row and subtract from third row, so I will have here 0 T2 plus T1. So, I will have T3 minus T1 T3 square minus T1 square, this is there, and minus I will have T3 minus T1 into T2 plus T1. So, if we simplify this ones, I will have, so this is T3 square minus T1 square minus T3 into T2 and I will have also plus T1 into T3 and minus T1 T2 and minus T1 square. So, this T1 square will cancel. So, I will have what? T3, okay, T3 can take common, T3 minus T2 and here I am getting minus T1 common, then I will have T3 minus T2. So, I will have basically T3 minus T1 into T3 minus T2 type of factor please. So, this entry is basically going to me like this one only, which is not equal to 0 please. So, this implies that the Saint matrix is invertible. So, this implies that C 1 equal to C 2 equal to C 3 equal to 0 is only solution, Okay. So, this implies that your L 1, L 2, L 3 is a basis, of V star. Fine. Now, I have one question here. I want to find a basis for the space V for which this L 1, L 2, L 3 will be dual. Now, we are to find a basis, say P 1, P 2, P 3 of V such that L 1, L 2, L 3 is the corresponding dual. That is L I P j equal to delta I j. So, I want to find that P 1, P 2, P 3 for which this relations. So, it is suppose double star. So, this relation will hold good. How to find it please? Okay. So, to answer this question, what I have to do? I will take, let P 1 is an element, of the corresponding basis such that L 1 P 1 equal to 1, but L 2 P 1 equal to L 3 P 1 equal to 0. Let, since P is a polynomial function of degree less than or equal to 2, so I can consider say P 1 is equal to something like A 0 plus A 1 x plus A 2 x square. So, this implies that L 1 P 1 which is equal to A 0 plus A 1 T 1 plus A 2 T square. So, this is equal to 1. L 2 P 1 which is equal to, again I will have A 0 plus A 1 T 2 plus A 2 T 2 square, A 2 T 2 square equal to 0, and L 3 P 1 equal to, will have again A 0 plus A 1 T 3 plus A 2 T 3 square equal to 0. So, this implies that I will have a system of equations like I will have 1 T 1 square, 1 T 2 square, 1 T 3 square, this into A 0, A 1, A 2 equal to 1 0 0. Let it is basically your A matrix into your A 0, A 1, A 2 equal to 1 0 0. So, already we have seen if T 1, T 2, T 3 are distinct, then this coefficient matrix is invertible. So, if I find the inverse of P, let P equal to A inverse, then the coefficient A naught, A1, A2 will be equal to what? P inverse into 1 0 0. So, we have to find the inverse of this matrix place. So, that once this A naught, A1, A2 is known from these equations, say equation 1, then I will be able to find the corresponding polynomial. So, P1 will be known to me please. Now, exactly same way I can also proceed for P2. Let P2 is equal to d naught plus d1 x plus d2 x square. So, that L1 P2 equal to 0. So, this 0 which is equal to what? Which is equal to I will have d naught plus d1 t1 plus d2 t1 square, okay, and L2 P2 equal to 1. This implies that I will have d naught plus d1 t2 plus d2 t2 square, and L3 P2 equal to 0. This is equal to I will have d naught plus d1 t3 plus d2 t3 square. Basically, I am getting what? I am getting again same 1 t1 t1 square, 1 t2 t2 square, 1 t3 t3 square, this into d naught d1 and d2 equal to what? I will have 0 1 0. So, this implies your d naught d1 d2, this vector is equal to again P inverse into 0 1 0. So, I can immediately calculate the coefficient of the P2 please. Similarly, for P3 I will have G naught, G1, G2. So, this will be equal to something again P inverse into 0 0 1. So, in this way we can immediately calculate corresponding polynomial where P3 which is equal to, if I write G naught plus G1 x plus G2 x square, then I will have the coefficient G naught, G1, G2 equal to like this thing please. So, P1, P2, P3 will be known. And any polynomials and any polynomial function of degree less than or equal to 2, say that is P, we can write P equal to, then P will be equal to C1 P1 plus C2 P2 plus C3 P3, but C1 equal to what? C1 equal to, we know P at T1 into P1 plus P at T2 into P2 plus P at T3 into P3 please. So, any polynomials can be written like this thing please. I hope you have understood how to find the corresponding basis for which L1, L2, L3 will be dual basis please. So, now let me consider the linear functional and subspace. Okay. Let V be a vector space over a field say capital F. Let F be a linear functional on V. So, F is basically mapped from V to capital F. Let dimension of V is n, then dimension of V star also equal to n, because the dimension of F equal to 1. So, this dimension of V star will be equal to n. So, this implies that dimension of range space of F will be at most how? Now, if F is a 0 functional, 0 linear functional, then the range space of F is 0 subspace of F. Okay. So, this implies null space of 0 linear functional is your entire space V. If F is a non-zero linear functional, then rank of F is 1 and nullity of F is n minus 1. If dimension of V is n. Okay. If V is a infinite dimensional vector space, then I will say that the null space of non-zero linear functionals will be 1 less than the dimension of the vector space V please. But since in the case of infinite, then there is no question of that one. So, I will simply say that for finite dimensional vector space, the dimension of the null space will be 1 less than dimension of V please. So, now let me introduce one terminology called hyperspace. Any subspace of dimension n minus 1 of a vector space V of dimension n is called a hyperspace. Sometimes it is also known as hyperplane please. So, this implies for a non-zero linear functionals on a finite dimensional vector space, V of dimension n, the null space of F is a hyperspace. Please. Let me introduce one more terminology, that is annihilation please. Annihilation. Let V be a finite dimensional vector space. Let capital S be a subset of V. Then the set of linear functionals which annihilate is called annihilator of S. They note that this set of linear functional which annihilate S is basically a subspace of vector space V star. Let me denote, let S naught is equal to set of all the f belongs to V star such that f of alpha equal to 0 for all alpha belongs to capital S. So, this is the definition of S naught, that is annihilator of the set capital S. So, if the set S is subspace, then also S naught will be annihilator of the subspace S. So, S no need to be a subspace, even if it is for subset, then also one can have annihilator, and the annihilator will be same place. The small results is like this. Let V be a finite dimensional vector space of dimension n over a field capital F. Let S be a subspace of V of dimension k. Then dimension of S plus dimension of S naught equal to dimension of V. How to prove it? Prove is also very easy. So, let me consider like this. Let alpha 1, alpha 2, alpha k be a basis of S. Then it can be extended by adding n minus k extra linear independent element to it to be a basis for the V. So, let B prime equal to alpha 1, alpha 2, alpha k plus 1 to alpha n be the basis of V. Okay. So, this implies there exists a dual basis B star which is consisting of F1, F2, Fn such that Fi alpha j equal to delta ij. So, according to our last results, I can say there is a dual basis B star consisting of F1, F2, Fn such that Fi alpha j equal to delta ij. I mean Fi alpha 1 equal to 1 and Fi alpha j equal to 0 when I not equal to j please. Okay. So, I have like this thing please. So, this implies for any f belongs to V star, I can write down f is equal to as sigma f of alpha j and f j, j equal to 1 to n, that is what we have already learned from last results. So, I can express any linear functionals of V star as a linear combination of this thing. Now, if f annihilate, let capital S implies f annihilate all alpha I equal to 1 to k. So, this implies that f can be written as a linear combination of f alpha j f j, j equal to k plus 1 to n only. This f1, f2, fn is a linearly independent set of V star, and so now this f k plus 1 to f n will be again linearly independent elements, and any linear functional f which annihilate capital S can be written as a linear combination of this n minus k linear functional place. This implies that the dimension of S naught equal to n minus k, and dimension of S is already given k. So, this implies that dimension of S plus dimension of S naught is equal to your k plus n minus k, which is equal to n. So, I see that dimension of any subspace S of a vector space V plus dimension of its corresponding annihilator is equal to dimension of V. In fact, if I consider any k dimensional subspace of the vector space V of dimension n or any finite dimensional vector space, if it is dimension n, then I will say that the subspace S can be considered as intersection of n minus k hyperspace also, which I am going to prove in my next class please. Thank you.